Hello everyone, and welcome to my video notes. I want to talk a little bit about this before I get into it. These notes are very similar to the ones we do in class. In fact, the notes part is exactly the same. Where the difference is I cut out a lot of the examples. I don't want to spend time on videos working out examples. So that's what class is for. If you miss a day, these videos are great to kind of catch up. Or if I miss a day, I might show a video in class. But they're not a substitute for coming to class and paying attention. You're not going to be able to ask questions from the video, and a lot of the examples that you might see on quizzes and tests aren't on these videos. So these videos are a good review or good supplemental material, but they don't replace the in-class notes. Okay, today we're going to talk about intermediate value theorem. This isn't actually a calculus topic. It comes up a lot though. So I want to spend this first day just talking about what it is and how we use it. It's actually a pretty easy topic. Intermediate value theorem. Well, what is the intermediate value theorem? In math terms, it says that for two values, a and b, and a continuous function. Let me circle that word continuous. Function has to be continuous. Then from every a to b, f of x takes on every value between f of a and f of b. So between every x value, you've got to get all the y values. Now, in other words, you can't jump y values on a continuous function. And I'll give you some examples of what I mean by that in a second. This doesn't mean that you can't go outside of that interval. It's just that you have to hit every value in that interval. Let's look at a graph of this. Or let's talk about some examples first, actually. If you start at rest, and then 5 minutes later you're going 60 miles an hour, that means that sometime in that 5-minute span you had to be going 25 miles an hour. Because 25 miles an hour is between 0 miles per hour and 60 miles per hour. You also had to be going 30 miles per hour, and 40, and 45, and 50, and 55. You also had to be going 10. That's what the intermediate value theorem says. You have to hit every point between 0 and 60, which are y values, between the x values of 0 and 5 minutes. Could you be going 65 miles an hour at some point in time? Yeah, you could. The intermediate value theorem doesn't say that you can't go outside of 0 to 60, but that you have to hit every point from 0 to 60. You buy a small tomato plant at Lowe's and plant it in your garden. When you first bought the plant, it was 3 inches tall. 3 weeks later, it's 20 inches tall. At some point, the plant was exactly 11 inches tall. Okay? So if I start at 3 and I go to 20, some point in time in there, the plant has to be 11 inches tall. It can't go from 10 inches to 12 inches without being 11 inches somewhere in between there. Back in the winter, you made a snowball and put it in your freezer because you are weird. You then decided to set it out in the summer heat and watch it melt again because you are weird. The snowball started with a diameter of 6 inches and completely melted over 2 hours. That means at some point in the 2 hours it had to have a diameter of 1 inch. Of course, if you start at 6 inches and it completely melts down to 0 inches, at some point in time you had to be 1 inch. I don't know where you were 1 inch. I don't know how long it took. I don't know at what time exactly, but I know somewhere between 0 hours and 2 hours, that snowball had a diameter of 1 inch. It couldn't go from 1.5 inches to a half an inch without hitting 1 inch in between. So those are all real-world examples of the intermediate value theorem. These are not examples, but let's talk about why. There are 100 people in a large room. An hour later, there are only 10 people in that room. At some point in that hour, there are exactly 35 people. It seems to make sense. If you start with 100 and you go to 10, at some point in time there has to be 35. But that's not true. It's not true because unlike plant growth or unlike the diameter of the snowball melting, this function is not necessarily continuous. Why is that? Because maybe 30 people left together. That's possible. You don't have to leave one person at a time. People can leave together. So it's possible to go from 40 people, and then 30 people leave at once, and you have 10 people. So there, at no point in time was there 35. It's not continuous. If it's not continuous, the intermediate value theorem does not have to apply. You have $100 in your bank account today. 1 week later, you have $300. At some point, you have exactly $250 in your bank account. Again, not necessarily true. Maybe you had $100 in there, and then you deposited $200. At no point in time did your bank account have $150 in it. It had $100, and then it had $300. This is not a continuous function. This function would look like this. It would be at 100, and then it would jump up here to 300. It's not continuous, so the intermediate value theorem does not have to apply. Okay? Corollary to the intermediate value theorem, and this is the one that you see most often. Given a continuous function and two x values a and b, and given that f of a is negative and f of b is positive, or backwards, f of a is positive and f of b is negative. Let's stop and think about that for a second. What they're saying is that you have two y values. One of them is a positive and one of them is a negative. Or the other way around, one of them is a negative and one of them is a positive. What does that say? If I go from negative numbers to positive numbers, and I can't skip any number in between, what number has to be in there between every set of negatives and every set of positives? You have to hit 0 at some point in time. Suppose that this is my negative number and this is my positive number. At some point in time, I don't know where, but somewhere in there you have to cross 0. If you go from a negative to a positive, at some point in time you have to cross 0. Now, could it happen more than once? Sure. If this was my negative and this was my positive, I could do this and cross 0 multiple times. The rule says that there has to be some point in there that you cross 0, which makes sense. If you're going from negative to positive, at some point in time you have to be 0. Not only negative to positive, but also the same thing holds true if you go from positive to negative. At some point in time, you have to cross 0. Maybe you cross it more than once. Maybe you only cross it once. But you have to cross it at least once. Let's take a look at a problem. The following table represents a continuous function. So it's continuous even though we can't see the graph. How many zeros must the function have? Not how many could it have. It could have an infinite number. But how many must it have? Well, let's take a look at this part right here. Nope, let me start back here at the beginning. I went from 6 to 11. Did I have to cross 0? No. I could have, but I don't have to cross 0 from 6 to 11. How about from 11 to 2? If I go from 11 to 2, do I have to cross 0? No. How about here? If I go from 2 to negative 5, do I have to cross 0 between 2 and negative 5? Yes. At some point in time between 0 and 1, 0, 2, and 1, negative 5, you have to cross 0. How about from negative 5 to negative 13? Do I have to cross 0 in there? No, they're both negative. How about here? Yes. To go from a negative 13 to a positive 7, you had to cross 0 at least once. How about from 7 to negative 1? Yes, I went from a positive to a negative. It means I had to cross 0 somewhere in there. And then lastly, no, they're both negative. So how many zeros does this function have? We don't know. But it must have at least 3 zeros. It might have 3,000. I don't know. I don't know what goes on in between here. But if it's continuous, then it has to have at least 3 zeros. Give a value of k such that a continuous function has at least 3 zeros. Well, let's just see how many it has from the numbers we know. Is that a 0? Not necessarily. How about here? Yes, that has to be a 0. How about here? No, not necessarily. So I already have 1 0. So I know I need a 0 from here to here, and from here to here. So I need to find a value of k such that from -2 to here is a 0, and then from here to -5 is a 0. Well, what kind of number do I have to put in here to make sure that this is a 0 and this is a 0? K can be any positive number. Any positive number for k. For example, if k was equal to 6, I can't go from -2 to 6 without having a 0. And I can't go from 6 back to -5 without having a 0. Okay? This was a problem off an AP test a couple years ago. So just be aware of that. That's not even a calculus problem. That's a simple problem. But if you've never seen it before, you can't do it. Okay, guys, that ends the first set of notes that we're going to do on the first day. Next time calculus really starts, we'll talk about derivatives. As always, if you have any questions with this, or you want to see more examples, or you want to talk about it more, come see me before school, after school, or during study hall. Okay? Thanks, guys.